Okay, and we now have our last speaker of the session.
Thank you. Hello, everyone. I'm Hanliang. It's my honor to introduce our JFP paper on calculating with contrast lenses. This is a joint work with Tang, Wenhao, Ruifeng, Meng, Wang, and Zhenjiang. So, program calculation is an established technique for reasoning about and optimizing functional program. A calculational framework typically consists of many calculation laws that transform programs into another form. These transformations are semantic preserving, but also have the extra benefits of proving intermediate data structures and reducing time and complexity. For example, we have this map fusion law that states that the composition of two maps can be fused into a single map, proving the intermediate structure produced by the first map. Note that here we use semicolon as the composition operator, indicating a sequential composition. So the composition goes from left to right. Also, we have fold fusion law, which is perhaps the most important fusion law, which states that under condition listed in the above, we can fuse a fold composed by another function into a single fold, again, avoiding the intermediate data structure produced by the first fold. We also have fold map fusion law, which states that a map composed by a fold can be fused into a single fold, and the list goes on. As a concrete calculational example, consider this string processing function that returns the capitalization of all letters in a string. The initial specification says that we first filter out all letters, characters in a string, and for each of the characters, we use two upper to perform the transformation. To calculate this program, we first express the program by using combinators like fold and map. And indeed, list filtering can be expressed by fold. In the next step, we apply the fold fusion law to attain a final program as a single fold. So the benefit of calculating programs is twofold. Firstly, the resulting program is more efficient as it avoids producing the intermediate list comparing to the original specification. And secondly, the initial specification is simple, whereas the final program contains a more complicated function f. However, since the calculation laws are semantic preserving, we prove that the final program is equivalent to the original program without looking into the complicated function f. So essentially, to calculate a program, one would first express the program as composition of combinator functions and use those calculation laws to perform program transformations. Being functions, those combinators usually have the expected nice properties of being total and compositional. So the lens framework is a leading combinator approach to bidirectional programming. A lens comprises of a pair of transformations, a forward transformation get that produce a view data object from a source data object. The view data object is subject to direct manipulation, and a backward transformation put will take a source and a possibly modified view and reflects the modification back to the source, producing an updated source data object. We use the type notation with double-headed arrow to represent the lens. In addition to functional behaviors, these two transformations need to satisfy a correctness property, which are these two round-tripping properties. The get-pull law states that no change to the view should be reflected as no change to the source, while the put-get law requires that all changes in the view should be completely reflected to the source so that the changed view can be successfully recovered by applying the forward transformation to the updated source. We are interested in whether we can develop a calculational framework for lenses as well. Specifically, can we develop a set of lens combinators and related calculation laws? Turns out it's challenging. As we will see soon in later slides, lenses are compositional, but many useful lenses are often partially defined. As mentioned just now, one big advantage of using lenses is their compositionality. Given a lens L1 from S to V and a lens L2 from V to T, we can obtain a composed lens from S to T. In the forward direction, the lens composition is simply a function composition of two get functions. In the backward composition, an updated T value is first put back by using the lens L2 and the original V value to obtain an updated V value, which is subsequently used to update the original source by using the lens L1. Now, besides functional behaviors, the most important things about composition is that it preserves correctness. Namely, if two lenses satisfy round-tripping property, then their composition satisfies the round-tripping properties. Despite being compositional, lenses are often partially defined. In this context, the term partiality links to round-tripping properties, which is a strong requirement to the put component as it needs to handle arbitrary view changes. A lens is partial when its put component cannot successfully restore consistency for certain inputs, even if the get and put functions themselves are total. The partiality can be inherent, where the get function is non-surjective, so there's no meaningful semantics, put semantics for value outside of the range of get. This partiality can also be of design choices. As an example, consider this definition of list mapping as a high-order lens. The put direction will first pick the head elements of both source and view list and apply the backward transformation on them. The rest of both lists are processed recursively in the same way. Now, if any of the lists are empty, the backward transformation will simply return the empty list. This lens is partial, as it cannot restore consistency when the view list is updated to be longer than before. As an example, assuming the component lens L is an identity lens, so the forward transformation of this map is an list identity. When the length of the view list doesn't change, the backward transformation simply returns the view list, and no law is broken in this case. However, if the length changes to be longer, the backward transformation will break the put-get law, as shown in an example. So we kind of have a feeling that this B-map construction is actually conditionally correct, since if you only allow limited changes or limited updates to the view, then the round-tripping properties are satisfied. But we want a formal way to describe this kind of conditional correctness. We're also interested in the compositional behavior of those partial lenses, and we want to answer the question of whether composition preserves correctness in this case. So in fact, in this work, our solution to the question before is that we extend traditional lenses with a pair of predicates to constrain the changes on the source and on the view, which we call the source and view contracts, so that partial lenses can be constructed correctly and composed well. Here, the view contrast CV is a predicate that takes two arguments, the original view obtained by calling the forward transformation get and the updated view, restricting the permitted value of the updated view in relation to the original view. The source contrast CS has a similar structure. It takes two arguments, the original source and the updated source obtained by calling the backward transformation put, specifying an invariant that must hold for source changes as a result of value view changes. Here, we explicitly write contracts around a lens variable to indicate that this lens has the corresponding contracts. More formally, a contract lens comprises a pair of transformation and a pair of relations. Together, they satisfy the following round-tripping properties. The get-put law now is conditioned upon identity source changes permitted by the source contract. This precondition can be understood as a weakened property that all contracts are reflexive. Namely, identity changes are always permitted. The put-get law is now conditioned upon view changes constrained by the view contract. The backward validity states that the value view changes imply that source changes will satisfy the source contract. Forward validity is again a weakened property that all contracts are reflexive. This property is crucial to prove composition correctness between contract lenses. So essentially, the view contract is the correctness condition of a possibly partial lens, and the source contract represent the effect of applying backward semantics on the value view changes. Designed in this way, contract lens has the nice property of being compositional. In general, given two contract lenses, L1 with source contrast CS and view contrast CV, and L2 with source contrast CV prime and view contrast CT, if the source contract of L2 implies the view contract of L1, then the lens constructed by using usual lens composition is still a contract lens. meaning that it will satisfy the round-tripping properties. And also CS and CT becomes the source and view contract of the composed lens. But to formally prove this, we again need a forward implication that is a weakened property that all contracts are reflexive. With contract lens, we can now talk about the conditional correctness of the bidirectional map we constructed before. Here we simply add the predicates equal length as the source and view contracts. One can verify that this lens now satisfies the conditional Peking law, that if the length of the view list doesn't change, then we have the usual Peking law. Also, if the view changes are subject to equal length constraint, then this lens guarantees that the source changes also subject to equal length constraint. In fact, the bidirectional map defined before is a high-order contract lens, meaning that its input component lens is also a contract lens, but we don't put any restriction on it. The input lens should have the source and view contract that are trivially true. Here, we use any changes to indicate the contract that are trivially true. We write contracts around the lens type to indicate a requirement on the input lens. We can go a bit more generic and put the different requirements on the input lens. This gives us a bidirectional map combinator that takes a component lens L with generic contrast variables CS and CV. The resulting lens permits only view changes that satisfy point-wise constraint, which is a little bit stricter than the equal length constraint, but also provides stronger guarantees on the source updates that the source updates always satisfy point-wise constraints as well. In this work, we have developed a set of lens combinators specifically for list data structure. For instance, we have developed a bidirectional fold as a high-order lens that permits any view changes if the input component lens permits any view changes. Additionally, we have bidirectional fold with stricter view contract, which guarantees that the source updates satisfy point-wise constraint, and so on. Targeting at those combinators, we have developed related calculation laws. For example, we have bidirectional map fusion law that states that the composition of two bidirectional maps can be fused into a single bidirectional map. We've developed bidirectional fold fusion law and fold map fusion law as well, and the list goes on. For more combinators and calculation laws, we refer to the origin paper. Now back to the calculation law example mentioned before. With the contract lenses and the calculation laws we developed, we were able to bidirectionalize the string processing function as a composition of contract lenses. Further, those lenses can be expressed by the combinators we developed, and eventually we can apply the bidirectional fusion law to fuse the entire program into a single fold. So to conclude, we have developed a bidirectional calculation framework specific to the list data structure, and please do check out the paper for more combinators and laws and their applications. We have also developed an actor library that formalizes all the contract lens combinators and calculation laws. That's so much for my talk. Thank you very much.
We have a few minutes for a few questions.
Okay, Patrick Jansson here, in this slide. So you had this the B map and so on. I'm not sure exactly the terminology, but if you map first, say, so you have a list of pairs and then you get another list out. Of course, you can require that the view doesn't change. And I realized that if you insert something in the view, it's difficult to invent the other component, the second component. But why not allowing deleting elements? Could you have a combinator which, if you edit a list, the first component of the list, and then removes one element that sort of removes from the input?
Do you mean a map combinator that only modify the first element?
No, well, I mean, if you have map of first,
yeah.
that seems to be a pretty common view. You have a database, you want to edit one column, it's like.
Yeah.
And I realized that for your current thing, you require the length to be unchanged. But if you would shorten the list, wouldn't it be reasonable to shorten the input list, or can you express that? That's basically the question.
Sorry, can you please replace the scenario? Yeah, I do understand that you want to perform that operation as a bidirectional map where the component length is selecting the first between a pair, right?
Yeah, and then the change of the list is not preserving the length, but actually shortening one, removing an element in the middle.
Oh yeah, you can update the list to be shorter. Yes, and in fact, the equivalent constraint here is not the most generic one. The most generic one is that, like, you can update the list in any way, so long as it cannot be longer than the original list.
Okay.
Yeah.
Do we have any other questions? All right, but then we can thank the speaker again.
Thank you.